this off. Hi, everyone. This is Jamie Sampson. Mandy, he and I together put together this presentation after reviewing the paper titled PointRend, Image Segmentation as Rendering. So let's go ahead and get started. So this is what we're going to talk about. I'll cover the first 3 sections. There is a notebook that has a nice little demo that we'll briefly walk through. After that, Mandy will walk us through the experiments and the results for 2 tasks that are covered by this framework and library, one being instance segmentation, the other being semantic segmentation. The difference between the 2 is that instance segmentation is like the output that you get from a framework such as Mask RCNN, where it will identify every instance, identify all of the classes of those instances, and generate a map for each of those instances. Semantic segmentation is a little bit different. What it does is for each instant type, as an example, people, a road, trees, it will generate a separate color for each of those instant types, and it'll give you a nice view of each instance type, delineated by different colors. So why don't we get started? Okay, some typical problems in image segmentation as it's currently done, via CNN or Mask RCNN specifically. There are a few things that make it not ideal. One is the Mask RNN CNN framework does a prediction for each pixel. Some of those pixels are important, as you can imagine. The ones that are defining the boundaries between the instances are very important, whereas other pixels farther away from the instances, not so important. Another is the label map. Tend to be relatively smooth and don't capture the details. A good example of that is if you take a look at the image to the right here, we've got output from a Mask RCNN. You'll see the fingers aren't very well delineated in the mask, whereas if you take a look at the PointRend option next to it, those fingers are delineated very well. Just a note too. So if you notice the resolution of the Mask RCNN is 28 by 28, and it's 224 by 224 for PointRend. That points to another feature of another advantage of the PointRend framework is it can generate higher quality, higher resolution masks using a fraction of the compute that's required to do a similar a similar resolution mask. That's why you'll see on the left again they point to 28 by 28, and the authors state that this resolution is a compromise between undersampling and oversampling. I believe I've used a higher resolution. I think I used 64 by 64 in Mask RCNN. It didn't, for inference anyway, it didn't seem to be that extensive. But getting up to the possibilities of resolution, the PointRend can do it with a lot less computing resource. And you'll see why as we go to the next slide. Basically, rather than estimating each pixel, it will do some sampling and it'll choose which pixels to estimate via DNNs and which pixels to determine the value on extrapolation. And the extrapolation is much less expensive than the DNN. All right, so this is just a quick slide describing the architecture, or I should say the approach. So the PointRend, the rendering part of that is some of these approaches were inherited from the computer graphics space. I don't know much about that, but the authors state that sampling, interpolation is used, and interpolation is used a lot in computer graphics rendering. So that's where some of this stuff is borrowed from. But ultimately, it's an architecture that can develop masks where the training and the inference is less computationally intensive. And that's because, as I stated before, it uses a sample of the points for the image for both training and inference. And the rest of them are calculated via interpolation. And because of this, and also upsampling, which we'll talk about a little bit later in a later slide, it can generate higher quality, higher resolution label maps than than a mask RCNN can. Okay, just briefly, let's review the architecture. So just like, and this slide is very mask RCNN centric. It's pretty close to what it would be like for a semantic network, which, or a semantic, God, I'm struggling on semantic. A semantic segmentation, but let's just talk about it in terms of mask RCNN. So you're gonna have a CNN backbone, just like you would in RCNN. And there are two components to the point estimates. First, there's a course prediction. And what that does is, it's a relatively simple model that generates a K-class prediction vector. It'll generate the vector for each of the possible classes. But again, this is very coarse, very low resolution, and it kind of establishes the global context. They also do a fine-grained feature map, and what they do is they grab layers from the backbone, from the ResNet in this example, and they use this to represent rich features. Then they combine the coarse predictions and the fine-grained feature vectors, and then they run a relatively simple multi-layer perceptron model, 3 hidden layers, 256 channels, and it outputs a sigmoid, so it will indicate what's part of, it'll indicate the boundaries of the mask. So the way this works is, this is an iterative process, and at each iteration, what they do is they upsample. So as an example, the first one might be let's say a 4x4 feature matrix. They will upsample to 8x8. They will go through the point predictions, and they'll run that through the multi-layer. So that they'll have a prediction at the 8x8. That 8x8 with the predictions will be input to the next iteration. We'll run through the steps again, output perhaps a 16x16, and that can be run up to whatever the desired resolution that your particular application needs. And again, the key point is that since we're not, our model, our CNN, has fewer parameters, so it's computationally a lot more efficient, and because of that, we can go to a higher resolution. And I think in some of the tests, it goes up to 224 by 224. Okay. So let's talk about the 3 steps in the process. So as I mentioned, it's kind of an iterative process. So it starts with the upsample. So you've got your 4x4 grid. It's upsamples to 8x8 in this example. It uses bilinear interpolation to come up with the initial values for each of the cells after the upsample. Then it takes an adaptive subdivision approach, and I guess this approach is fairly common in the computer graphics space. But so what it does is it calculates this high probability of how can I say it? It identifies the cells that have the most difference than their neighbors, which likely would identify the boundaries. And what it does is it takes a sample of those. It runs through the point predictions using the coarse grained and the fine grained that I described earlier, and then it uses those point predictions and gives you as the last step the output mask at the 8x8. But again, this is an iterative process, so through each iteration, the resolution increases and the accuracy of the mask increases as well. Okay, so the slide that I showed you previously talked about how inference works. Just a little bit of an adjustment for training. So I described an iterative approach. That iterative approach just doesn't fit very well into the feed forward back propagation paradigm of training a CNN. So they do it a little bit different for training purpose. So what they do is they establish an N, which is a number of points that will be sampled. They establish an oversampling factor, which is just K, and K is a number greater than 1. And the other parameter is beta. And you can think of beta as the percentage of uncertainty. And as I mentioned before, that percentage is higher at the boundaries. So what they'll do is they will bias the sampling such that they sample more points around the boundaries, and then away from those boundaries, they will sample just uniformly. So what these pictures just show are just just some variations of the K and the beta. So if it's totally uniform, it looks like B. If we add a KF3 and a beta of 0.75, you can see most of the points are around the boundaries. And at K equals 10, beta still at 0.75. Same phenomenon. We get more points away from the boundaries as well. So this is used as as kind of the input into the into training the model. Okay, so step 2 is to extract the pointwise representation. And as I mentioned before, this pointwise representation, the input to it is both fine-grained features, and those fine-grained features are come from a feature vector at the sample points from the backbone CNN, one or more layers. And this provides the detailed feature information. The coarse predictions come from a very coarse estimate of the mask. The example that they gave was 7 by 7, and you know, for each point, the estimate will be for, you know, it's k-dimensional, so each dimension represents the class, the possible classes, and the coarse prediction is kind of like a standard CNN parameter. So supervised training, you know, will establish, you know, the model for the coarse predictions. And in essence, what this provides is region of the grid specific information. So the theory is that the combining of the detailed features with the region specific information, going through this iteratively gets you a better and better mask. Okay, and then the last step is the point head, and that's essentially a relatively small neural net. They call it a multi-layer perception model. The one that they used in their example, I believe it was 2 or 3 hidden layers. The weights are shared across all points in all regions, and it essentially takes the concatenated coarse and fine features and generates the estimate for the mask. And again, this can be trained kind of the standard way that you train a CNN with a cross entropy loss. Okay. Okay, let me briefly show you what this particular little tutorial looks like. And I'm not going to run it. I'll just show you the results real quick. So the paper ships with a library. It's called Detectron 2. You know, it just grabs an image of an airplane here, creates 2 separate configs. One config is for the masked RCNN output. The other config is for the rendering model output. And then we visualize both models. So the top model is the point rendering output from the point rendering model, and the bottom is from the default mask RCNN. And as you can see, just visually, the top one does a much better job in terms of identifying the mask. We see a lot, especially on the bottom of it. We see a lot of, especially around the tail. You see a lot of the area. I shouldn't say a lot, but you see some of it being missed. It just isn't as clean as it is in the top image. Okay. Let's see. And this provides a few graphics that walks through the course prediction, the iterative process. So this is what a first iteration could look like. Resolution is 7 by 7. Sample points over that course prediction. Run inference. And it takes a pretty big jump here, as you can see, but because we went from there's our 7 by 7, more iterations get us up to 28 by 28, 56 by 56. You can see now the points are starting to, you can kind of see the boundaries are starting to be identified. 112 by 112, we're getting much better as well. And then the final result at 224 by 224, you can see the boundaries are pretty well defined. And that's about it. I'm going to hand it over to Mandy, who's going to walk through the experiments and the results that were published in the paper. So go ahead, Mandy.
Okay, thank you, Jamie.
Sure.
So this paper, they have two experiments. So we will first go to look at the instance segmentation. For dataset, they use the first dataset is COCO dataset for instance segmentation. COCO has 80 categories. A lot of them are everyday, those everyday categories. They have a training and a validation data set already separated in very fine folders. Under COCO, there is a sub data set is called LVIS. This data, the paper also evaluated on this data set because LVIS has a better quality of segmentation annotation. So we will see in the later part that for better, higher quality instance segmentation annotations, the average precision will be actually higher. The second data set is cityscapes. It is a city scene in, I think it's in 50 cities. It has 8 categories. It's an egocentric street scene data set. You can see from the right side bottom, that is how the after segmentation, how it looks like. So this data set actually has as good as LVIS data set, as good as regarding the annotation quality. The quality is very high. So on the right side, the 3 pictures, the first one is the regular COCO data set. The second one is the LVIS. It has more pixel-wise, more high quality instance annotations. The bottom ones, the cityscapes. And then the paper will evaluate on the mean IOU intersection of unit to report on the average precision on that part. So the training and the inference, it uses the architecture that Jamie just talked about, and as well as the same steps that he introduced. So for training part, the paper did some pre-processing with simple pre-processing, horizontal flipping and scale. But on inference, there's no pre-processing. For training part, for train the PointRend, as we mentioned, we will, the PointRend needs to sample some specific point for training. So they choose to sample 14 to the power of 2 points using the bias sample strategy, which means that to sample those boundaries, those uncertainty points. So they choose n is 14 to the power of 0.2. Remember, we in the training part, we use the oversampling strategy. So the oversampling ratio k is 3. So it's 3 times of the selected number of points. And the uncertainty ratio is 0.75. So basically 75%, if it's uncertain, will be sampled into this point. And so again, for the point-wise uncertainty measure is to calculate the distance between 0.5 and the probability of the ground truth predictions. So that is to measure how uncertainty the point is. That is from the course prediction. Remember, we have a course prediction. And the cross-entropy loss, we have the predicted box for K classes. We also have the masks, which is pixel-wise predictions. Each pixel belongs to, they have different mask, belongs to this part, this class or that class. So the loss function is actually the sum of these two losses, for losses for predicted box and the average loss for the predicted mask over all the points, because it is pixel-wise the prediction. For inference, the paper used adaptive subdivision techniques, just like what Jamie mentioned. They have upsampling. For example, they start from the 7 times 7 feature, and then during the iteration process, it will upsampled to, for example, 14 to 14 until finally reach a set predefined resolution. So in this experiment is to reach 224 times 224 resolution. So they adaptively subdivide and then select the points and predict. So in each step, they select the points for the uncertainty point and update those most uncertain points based on the difference, the absolute difference. The paper reports several results. For the main result, it's to report the average precision. We can see the result is to compare mask RCNN. Here it refers to 4x curve weight, that is for mask RCNN's mask head. So compare with mask CNN and PointRend. Because mask RCN usually to predict on a smaller resolution. So you can see 28 times 28. Even on this smaller resolution, we can see PointRend on COCO dataset for the average precision, 36.1 is 0.9 increasement in the average precision. And but because PointRend using this adaptive point selection strategy, its computation is more efficient, so it's able to predict on a high resolution. So here PointRend has 224 times 224 predictions. So we can see on that part, the average precision is increased even more. You can see for COCO dataset is 1.1 increasement, but for the AP star, which is to predict on the LVIS, and also the AP for on the very right side of the first table for cityscapes, because these two data sets has better high quality annotation. So you can see the precision reach to 2.1, 2.8, so it's even better. That's the report from this. The second table is a report the computation performance for PointRend. We can see PointRend has higher 0.9 flops per second, has more efficient computation, and also enables more activation point, 0.7 millions. So, so here on this report, it's mainly to show that its outperformance the mask RCNN on different data sets, higher, better quality of annotation will facilitate better average precision. And also on the right side, from the picture, you can see the cat's feet. Those edges, airplane, those edges, relatively, maybe not relative, even on the boundary, area can perform very well. The higher resolution on the bottom perform better on prediction, drawing the fine line on the boundary, better than the smaller resolution. Here, the result to report the subdivision inference, how that performance during the inference process. So the main idea here, if you look at the left picture, it shows, again, the same idea is higher resolution will improve the result. Predicting on higher resolution will have better results. So on the table, we can see that the first half is the number of sample points is fixed, 28 to the power of 2, but the output resolution is increasing from 28 times 28 to 224 times 224. We can see the average precision is increasing on COCO dataset cityscapes, but we will see a stop at some point. So the same thing happens when we set the output resolution to 224 times 224, but we increase the sample point for the uncertain point. So we increase, but we can see it will saturate on some level of point. So here, the paper reports that the average precision saturate at a certain point. And these two parameters can be kind of fine-tuned or trained for different data sets, for different use cases. And it also reports that even though AP, average precision saturates, but it's because it saturates because the point selected we select first with the most ambiguous one, most uncertain one, and then with less uncertain one. So that's the point strategy impacts of those two parameters. But for objects with more complex boundaries, these two parameters can be beneficial and can be fine-tuned. It also reports some ablation experiments. So mainly from the table, we can see is experimented from a simpler backbone, R50 FPN, to a more complex backbone. So this paper found is currently training on ResNet 50 plus the FPN, which is a feature pyramid network. Training on this backbone kind of underfits the COCO dataset. So the paper suggests that a longer training time on a larger model will perform better for this PointRend. The second experiment, they actually just spent very short time to talk about is semantic segmentation. It will be more brief. The data set is using Cityscape semantic segmentation data set. It has 19 categories. It also have training validations very clearly. And then the paper is evaluated the mean intersection of unit of 5 trials. So it's report average IOU. The architecture, again, very consistent, is use the same architecture that Jamie talked about, and also the same architecture of the instance segmentation. The backbone is different. They choose to reproduce 2 papers as their backbone, and then add on with the PointRend. 2 backbone deep lab with 3 using ResNet 103 And semantic FPN using standard ResNet 101 is an encoder-decoder architecture. The implementation here is follow the same implementation as we introduced before. So have a course prediction and to sample those uncertain points and iteratively to upsample and to update the label map and fine-grain the feature from their chosen layers for different backbone. And for training, they sampled as many points as they are on that feature map, and they use the same K and the beta for point selection. So during inference, they choose this point, number of points, 8,098, until reaching the input image resolution. They actually predict on the original input image resolution is 1024 times 2048. So the result, according to their report, is PointRend here for different backbone, they all increase 1.2, 0.9. Yeah, so that's their report. So basically, they report that PointRend refines the prediction scores for the areas with course prediction, where course prediction is not sufficient. So they report with higher mean IOU. So going back to the computation efficiency, that by sampling the points adaptively, selectively, so PointRend, they can predict on the original image resolution size. For example, for the 2 million points, but they only make predictions for very small points, 32K. That's basically what they report.
Okay, so yeah, just briefly, the conclusions are, what the authors stated they were looking for. Better results, higher resolution, more accurate masks, and because of the sampling, they were able to do this with fewer model parameters and significantly less compute time. I believe for the experiments that Mandy talked about, especially for the image segmentation ones, I think they talked about a 30% or no, 30 times decrease in compute for this versus what it would take for similar resolution on mask RCNN. And on a personal note, so I used mask RCNN for image segmentation for the challenge for the fellowship. And if I would have known about this library, I probably would have gone with this and had a little bit better image segmentation results. As I mentioned, there's a GitHub repo that has the implementation and instructions. So it's not in there now, but I'll add a link to that to the deck. Does anybody have any questions? Going once, going twice.
Just a quick question.
Sure.
Did you try to use this on any input images that had a lot of overlaps?
I did not. The papers talked specifically of overlaps and spent a little bit of time talking about the approach that it used for which instance to associate that particular point with. So I can tell you the framework accounts for it. I can't tell you exactly how off the top of my head. I'd have to go spend some more time in the paper, but they did address that. Yeah,
Gotcha. Okay, thank you.
sure. Any other questions? All right, thanks everybody.
Thank you.
Have a good night.
Have a good night too.